embryo is undergoing gastrulation in the bottom. So I think it's fair to say that biological systems are the most richly textured form of matter in the whole universe. And if anyone has something more richly textured, I guess we have to define that, but then let me know. But I suspect we're going to have to wait until we find an alien life form, and maybe it'll be more highly evolved or something. But that's a call to arms. I mean, in terms of physics, we suspect that there's going to be entirely new physics in biological systems by trying to study the principles that govern self-assembly. So what makes biological systems so interesting, one of the features that makes them so interesting is that there is a wide span of length scales involved in sort of hierarchical self-assembly. So you can think of blocks, protein and RNA interactions, let's say. And then the function, the assembly and function of those things then dictate cell behaviors, tissue behaviors, and organism behaviors that ultimately can build soft, squishy robots like you and I. Now, what's interesting, I think, about this is that we actually know a fair amount, and certainly not everything, but we know a fair amount about the physics that governs self-assembly at the nanometer scale, so at this kind of smallest scale that I represent here of biological self-assembly. We can think about structural biology models, protein folding models. We have a pretty good conceptual framework for understanding things at that level. If we go up to the highest length scale, sort of what I'll call sort of macroscopic length scale, we can think about continuum mechanics models, the kind of cell vertex models that people think about in collective tissue behavior, or even if you want to stretch it, you can say sort of physics-inspired behavioral models. So we can say something about what's happening at that scale. The length scale that I want to talk about as the focus of the discussion today is this mesoscale, at the sort of micron length scale, structures within living cells. And I would argue that we have very little understanding of the rules that govern assembly at that scale. So I'm going to try to tell you about some of the ways we're thinking about that. A lot of the work in my lab and in this field that I'm going to tell you about is inspired by soft condensed matter systems that are non-living, but have some features, qualitatively at least, that are similar to biological systems. They're squishy and they involve macromolecules, things like polymers that can give rise to emergent behaviors, viscoelasticity, and so forth. So we're thinking a lot about the ways in what we learned in soft non-living matter and how we can take some of those insights into living cells and ask, can this give us new insights and new knowledge on how cells are organizing their contents? So if you think about what's happening inside living cells, that picture, the movie I showed you in the beginning, the simulation of all these molecules that are interacting, one of the ways, sort of high school biology textbook picture of how the cell organizes its contents is through organelles. And so many of you probably remember from high school biology the organelles with these funny names like endoplasmic reticulum, Golgi apparatus, and so forth. So essentially all the ones we learned about in high school biology are membrane bound, and they're to some extent vesicle-like. They're like little soap bubbles that compartmentalize the inside of that, that compartment from the outside, and so that kind of makes a lot of sense. But we think that that's probably just really the tip of the iceberg in terms of the way compartments form inside the cell and the way in which the cell organizes its contents. Turns out there's a whole broad class of membrane-less organelles, so bodies that are large-scale assemblies of thousands or millions of molecules that are forming coherent structures inside cells that play a broad range of biological roles. I'll tell you a little bit about these germline P granules in the top left here. There are things like processing bodies, signaling assemblies, and there's an array of these structures inside the nucleus, at some compartments of the nucleus. And in fact, I think it's probably fair to say that most of the bodies inside of the cells, most of these kind of organelles that one sees, are in this category of membrane-less. So it's not, it's not sort of a small subgroup, but in fact, maybe most of the organization is mediated by these kinds of structures. And so I started thinking about these in the context of this problem, which these structures are called P granules, and they're implicated in specifying the lineage of the cell, so the fate of the cell, whether the cell is going to form a neuron or a gonad or something else. And so these structures are implicated in specifying the reproductive organs of the gonad of the C. elegans worm. And what's interesting is initially, after fertilization, you can see that they're distributed throughout the embryo, so these green puncta distributed throughout the embryo. But as the embryo starts to polarize and develops a distinct anterior versus posterior axis, these structures end up on one side. And when the embryo then divides in two, only one cell, the cell on the right, gets those structures, and that's the progenitor germ cell that goes on to make reproductive organs in the worm. And so this process, we've learned a lot about how it works. It's mediated by gradients of molecules that are kind of morphogens that control the segregation of P granules into the embryo posterior. What's really fascinating about how this works is that these structures of these P granules we discovered are liquid-like assemblies of RNA and protein. So despite the name as a granule, they're not little pebbles. They're actually condensed liquids. And you can see that in this movie where we apply shear stresses across the tissue in a very kind of low-budget rheology experiment. We just basically squash this tissue and do shear stresses. And what you can see is these P granules flow and drip and wet and coalesce with one another. And so this led to a model wherein the segregation of these P granules into the posterior end of the embryo is a kind of phase transition or a liquid-liquid phase separation process, just like what Sharon Glasser was telling us about in a non-biological context. So the idea is that the anterior-posterior axis of this embryo spans the two-phase boundary such that the posterior end of the embryo is in a two-phase region where these condensed liquid states of RNA and protein are stable. And since we first put forth this model, there's a lot of data supporting this, and it's a very rich problem, and there are many non-equilibrium features which the cell is very much out of equilibrium. You can see already from the gradient that drives this assembly. So this idea of condensed liquid states inside the cytoplasm and phase transitions driving organization inside cells actually has a long history. We started to discover papers back in the literature as far back as 1899. Pioneering interdisciplinary biologist E.D. Wilson had some of these ideas about the physical nature of the cytoplasm, and he described the cytoplasm or the protoplasm as a liquid in the form of an emulsion consisting of these suspended droplets. In fact, we've known that biomolecules can undergo phase transitions for many decades, and there's a lot of work with structural biology where trying to induce proteins, for example, to crystallize such that you can do X-ray scattering. Phase transitions have also been suggested to potentially play a role in membrane organization, and so there's kind of hints of this in the literature. And it has started to become apparent that these kind of phase transitions are ubiquitous within the cytoplasm and the nucleoplasm, the contents of the cell. There's literally dozens of different or really at this stage, hundreds of papers over the last several years that have come out suggesting that liquid-liquid phase separation is implicated in processes, ranging from mitosis to self-signaling, postsynaptic densities that mediate connectivity in neurons, and essentially, without exaggeration, I would say almost every biological process that's happening in a cell, there's some connection to liquid-liquid phase separation now that has been described. So we're really interested in this process, phase separation, and how it is occurring potentially to organize the contents of the nucleus. So the nucleus is where the genome sits, and so we're all familiar from 23andMe or something, with the idea that our genes are dictating phenotype. What's something that you may not appreciate is that every one of your cells, so this is actually a picture of my daughter when she was first born, every one of her cells has the same genetic code, the same sequence of base pairs that are supposed to dictate the phenotype. And yet she has dozens or hundreds of different types of cells that make up her body. So each one of those cells, its phenotype is supposed to be dictated by the genome, and yet you get totally different cell types with different shapes and different functions. So how does that work? Well, it turns out that it's becoming apparent that these kinds of condensed liquid states are like little dewdrops that are sitting on the grassy genomic landscape, and they're playing roles in mediating expression of genes. And we started to refer to this as a liquid epigenome. So there are many different types of these condensed liquid states which we think are doing this inside of cells. Structures like the nucleolus, which I'll tell you about, which controls ribosomal RNA biogenesis, so the protein translational machinery inside of a cell. Structures like nuclear speckles, which are regulating splicing, so how genes are being cut and cutting out introns, and so forth. And Cajal bodies, which are also playing roles in the regulation of expression of genes. So we started studying this with a postdoc in my lab, Steph Weber, who's now a faculty member at McGill University, and she was able to show that the nucleolus, so this structure that's inside the nucleus, the nomenclature is a bit unfortunate, so the nucleolus, and it assembles around these particular genomic loci that make the ribosomes. And she was able to show some evidence that the assembly of the structure seems to follow a phase boundary. This is we could change the concentration, and the higher the concentration, the more material condensed out of the nucleoplasm. We can also look at the dynamics of the assembly of these droplets and show that there was coarsening of nucleoli around those transcriptional sites that was consistent with sort of classic modeling approaches. So this is the Cahn-Hilliard equation, which is a kind of diffusion equation, except it's uphill diffusion. I was going to make a point about how entropy can only drive things downhill in Fick's law, but that may be totally wrong now that after Sharon's talks, I'll hold my tongue on that. But it's exciting to think about. But generally, one thinks about diffusion down concentration gradients driven by entropy. And so if you want something that's uphill diffusion, you would have to have some interactions, something beyond just entropy. And that's what's in that formalism. What's different here, though, is that we have the presence of RNA through the transcription at a particular genomic locus, and that's why the droplet in the middle wins out. Another system that we've been using to probe this idea that liquid-liquid phase separation is important in the nucleus, in particular with the structure of the nucleus, is the Frog oocyte system. It's really powerful because it's a single cell. It just grows to be very large. It grows to be about 1 millimeter in size. So it's a single cell that you can hold in your hand, and it contains a nucleus that is similarly large. You can also see it with the naked eye. And inside that nucleus, there are hundreds of these bodies, hundreds of these nucleoli that are sitting there and can be mechanically probed and tested in other ways. And so this is actually one of the first systems we started studying. And we showed after the pigranule story, and we showed that these nucleoli really are have classic liquid features. This is a liquid bridge rupture after they start to fuse, and we managed to pull them apart. What's an interesting feature here is, again, there's signatures of non-equilibrium, the importance of non-equilibrium in cells, because if we remove ATP, which is sort of the molecular battery inside the cell, then the apparent viscosity of these structures goes up a lot. So they tend to fuse much more slowly, and their dynamics are slowed. So that's something that we're kind of actively studying. First graduate student in my lab, Marina Ferrick, who's now a postdoc at the NIH, came at this problem and started thinking about, asked a very simple question, which I'm a big fan of asking very simple questions at the outset of a project. And so Marina asked the question, well, if these are all droplets, why aren't they all coalescing? What's keeping them from all forming one mega droplet, like in salad dressing, if you shake up the bottle and come back? And so what Marina found was that inside this nucleus, there's a scaffold which is formed by an actin network, which is very interesting because it's a nuclear actin network. We're used to think of actin in the cytoplasm. And that actin network supports these droplets and keeps them from coalescing together. And what Marina found is that if she disrupts the actin network, these droplets actually do all coalesce. What we expected was going to happen was that they would all diffuse around and bump into each other, but what we found is they actually sediment under gravity to the bottom of this nucleus. And that was pretty surprising to us because I had actually been teaching in class how gravity is negligible in cells. And so Princeton didn't fire me, so that was good. But the calculation you want to do is you want to calculate this sedimentation length scale, which is essentially reflects the competition between entropy, which wants to mix up the system, so sort of captured by kT, and the gravitational force, mg, or here expressed in terms of a buoyant mass. And what's interesting here is that the cell has grown so large that it's actually exceeded this gravitational length scale. So that's like the equivalent of climbing a mountain in Bolivia and you can't breathe, right? The physics is the same. You sort of cross this length scale. And in fact, if you do this experiment, you wait overnight, you do find one single large droplet. And so this is the world's record nucleolus. It's about 100 miles bigger than most cells, so it's this giant thing. So the other thing that is really interesting about this work is that Marina found when she was doing these experiments and inducing this coalescence by disrupting the scaffold, she found that there are subcompartments of the nucleolus that actually themselves also coalesce during this large-scale nuclear coalescence. And so I'll show you this movie. The green shows an interior compartment that's characterized by this protein fibrillarian, and the red is this outer compartment characterized by protein nucleophosmin. And what you can see is that as these nuclei start to coalesce, the inner core also coalesce. And one has a sense that what you're seeing here is a kind of liquid within a liquid, as you can see in these higher resolution images on the right. And in fact, that's exactly what what we think is going on, we were able to show that we could reconstitute this liquid within a liquid assembly in vitro with purified components. What's remarkable about that in vitro reconstitution is that the core shell architecture is maintained. So these green proteins, fibrillar in particular, is on the inside and nucleophosphate is on the outside. And that, it's known from multi-phase liquid physics that the droplet with the higher surface tension with respect to the surrounding fluid will be engulfed by the other droplet to minimize that surface energy cost. So it's basically, if the high surface tension, surface energy, then if it's engulfed by the other droplet, that interface will go away and the energy will go away. And so we were able to do some surface contact angle measurements and surface tension measurements to show that that was consistent. It was also consistent with computational work that we did together with Rohit Papu's group at Washington University in St. Louis. So we like thinking about this because there are dozens of different types of these structures, and often they do have subcompartments, or there seem to be multiple liquid-like phases, which includes things like the stress granules. So we're interested in this idea that the relative surface tensions again structures the contents of these other bodies. There are other there are other bodies that don't interact at all. So they're not engulfing one is not engulfing the other, but they're not fusing or coalescing or interacting at all. And so we think that reflects a high surface tension that would be associated with the interface between those two. Again, it's known that in multi-phase liquid systems you would have complete exclusion of those droplets. There are other biological systems where there's partial engulfment of the droplets, one partially within the other, which is associated with sort of relatively more equal surface tensions. And things like this beautiful image of the Cajal body and the attached structure is called the synerposome, which I always think is such a cute name, especially for something that looks like Mickey Mouse here. But this is a case we think of a partially engulfed liquid. So I haven't said much yet about the molecular driving forces that are at play here. It turns out that many of the proteins that are driving phase separation are referred to as intrinsically disordered proteins. So the proteins that are conformationally heterogeneous. So I think everybody knows that proteins are linear polymers. They're linear chains of amino acids. But we generally don't think of them as polymers because we think of them as having a compact three-dimensional shape that dictates their function. But it turns out that many proteins are actually conformationally heterogeneous. So rather than being folded into a single compact shape, they're actually sort of fluctuating around. And I'll show in this movie, this is a simulation of a protein like this, one of these intrinsically disordered proteins, or IDRs. These are closely related, by the way, to what are referred to as low complexity sequences or prion-like domains. And so we and others in the field over the last few years have been intensely focused on these IDR proteins that contain IDRs, because when you purify these proteins and look at them in vitro, what you find is that they readily phase separate into these condensed liquid states, which we think corresponds to the same kind of molecular driving forces as the corresponding structure in the living cell. So this includes proteins like LAP1, which is one of a set of important IDR-containing proteins, the P granules, these germline specifying structures that I told you about at the very beginning, and also with nucleoli in the bottom two examples. And then this example, the yellow droplets, that's from a fungus. So these are just a few examples from our work, but there are really many dozens at this point of intrinsically disordered regions which are thought to drive phase separation. Another key molecular architecture of proteins that are driving phase separation is oligomerization. So a lot of the proteins, and we just really started to fully appreciate this pretty recently, is that a lot of the proteins have they'll have these intrinsically disordered regions. This is a linear representation of the domain structure of a protein. You'll see that blue intrinsically disordered region in the middle. On the left is what's commonly seen as an oligomerization domain. So that could be a dimerization domain, so homodimerization, or the protein I already discussed, nucleophosphate, it has a pentamerization domain. And so some sort of self-interaction that can be RNA binding domain, and so RNA is also in the mix here in many cases, and DNA can be as well. And so we started thinking about these architectures where you have oligomerization and intrinsically disordered regions which are interacting with themselves, we think, in a sort of weak multivalent fashion to drive phase separation. The issue in the recent developments of this field is that there have been very limited tools to study phase separation, particularly in the context of a living cell, embracing the full complexity of the cell. And so my group has been investing in developing technologies to be able to probe and control phase separation in living cells. And this involves an effort from a number of individuals who are shown here. In particular, Youngdae Shin, who's a postdoc, who's now a faculty member at Seoul National University, who really got this work started. It's been continued in next generation versions of this by a postdoc Dan Braha, graduate student E.J. Chang, and we benefited enormously from collaborating with my colleague Jared Tocher. And the idea with these systems is we're taking advantage of optogenetic proteins. So these are proteins typically borrowed from plants that can interact in a light-dependent fashion. So you shine light on these proteins, and something changes about their conformation that can open up binding pockets or interaction domains. And so the idea was we would have a light-dependent oligomerization. And so I'm going to show you a little bit about some of these systems. The first generation is this octodroplet system, and then we have a correlate system and a Cas-drop system. I'll tell you about the latter two. So the correlate system is really powerful. What it is it's built around a self-assembled scaffold, a 20-former. We're primarily using this protein self-assembly ferritin, and we've engineered each of those subunits to have one of a light-dependent heterodimerization domain. The other, the light-dependent binding partner, the other of the heterodimerization domain, we hook up whatever protein we want to recruit to that core. So the idea is we shine light on the system, and then we get this core that now is decorated with the interacting domains that typically have intrinsically disordered regions. So I'm going to show you these cells that are expressing these constructs, and we shine light on them, and you see that you get phase separation within the nucleus of these cells, and forming these condensates within the nucleus. You can have a lot of fun with this. This is toggling the light in time and asking questions about reversibility. And of course, since it's light, we can shine the light wherever we want and make pretty pictures. This is a 3x3 array of droplets, and that's Evil Droplet Man, as you can see. So we are having a lot of fun with this, and there's a lot of sort of non-equilibrium physics we're exploring. If you induce state separation in one part of the cell, what happens to the other parts, and things like that. One of the things that I'm particularly excited about is we've seen in the previous talks different kinds of phase diagrams, discussion of the rich phase behavior, the different crystal lattices associated with different regions of the phase diagram and so forth. This is a phase diagram of steel. So this is kind of, in some ways, it's a cornerstone or bedrock of materials physics, of kinetic matter physics. We try to be quantitative about the interactions and the underlying and the phase behavior. In biology, we still don't really have anything like that. So this is a schematic of what we think might be happening, where you have molecules that condense into liquid state and then we think can solidify. But we really don't have anything like that. But these optogenetic systems allow us to start to map phase diagrams in cells for the first time. This is a phase diagram that has this kind of characteristic binodal inverse paraboloid shape that is commonly seen in polymeric systems. And so the solid red circles are cells at those concentrations and the oligomerization state that do phase separate. The open red circles are the ones that don't phase separate. And these other points is the concentration of the condensed phase and the concentration of the dilute phase. And so we can explore this. We can start to ask questions. Do we see nucleation and growth? And we do. We see things like spinodal decomposition. We're starting to be able to define the spinodal. And we also see some evidence for gelation boundaries that cut through these binodals. And that's really interesting because many of these proteins that we're studying are also implicated in neurodegenerative diseases like ALS. So that's Stephen Hawking disease and Alzheimer's, for example. So in the remaining time, I just want to tell you about some of the ways we're using these kinds of tools to probe the content of the nucleus. There's been intense interest in the last several years in what's happening with these structures in terms of regulating gene expression and organization of the genome, but we really have no idea still what's going on. And a lot of that, I think, is because of this lack of tools. And so we feel that we're positioned to be able to answer some of these questions. What really are these droplets or these condensed liquid states doing in the nucleus? How are they interacting physically with the genome to regulate the expression of different genes, or to control the three-dimensional organization of the genome, which dictates its expression and function? So to get at this, we developed this optogenetic system, which is called Cas-Drop. It's built around the CRISPR-Cas9 revolution that you may have heard about, that allows you to sort of direct things to individual genes. And what we've done is taken that Cas9 and hook up to it a light-dependent oligomerization platform that allows us to drive phase separation at a definable programmable genomic locus. And so here is these are telomeres labeled in white, and then I shine light on the system, and you can see we get phase separation at those defined genomic loci. And so we can study the nucleation and growth dynamics of this, and we get off-target droplets if we ramp up the saturation too quickly, and so forth. In doing these experiments, we noticed something really interesting, which we're still trying to wrap our heads around and understand. But in doing these experiments where we see some of the off-target droplets being nucleated in control experiments, we don't guide the Cas9 to a particular locus. What we noticed was that the droplets, as they grow, they tend to exclude the genome. They tend to exclude chromatin as they grow. And I'll show you movies of this. What you're going to see is holes starting to appear, and those holes will appear exactly where the droplets grow. And so you can see that here. I can play this movie again. It's sort of fun to look at. But basically, we've got little black holes that are forming inside of the nucleus as these droplets exclude chromatin. And so what's been something that we're really interested in is what does that mean mechanically when you have coupling between phase separation and the mechanics of the genome? After all, we think of our DNA as software, but it's also hardware, right? It's a physical object with a persistence length and so forth. So it's a kind of entangled polymer network that has some viscoelasticity. And the elastic component of that network can actually contribute to the overall energetic calculation if we're thinking about whether these droplets will form, where they'll form, and so forth. We were inspired. I wanted to highlight. We were inspired by this beautiful paper in a non-biological system by Eric Dufresne's group, and started to look for these effects in our system. And I'll show you that that's what we think is happening. There's a mechanical effect. And the reason for that is, I should go back and just show you, the idea here is that if these droplets are trying to nucleate in particularly stiff regions of the genome, then they're going to have a hard time compared to the softer regions of the genome. And it's known that there's a lot of heterogeneity in the mechanics and the compaction state of the genome. So this is the case where we try to nucleate droplets within a dense, what's referred to as heterochromatic region of the genome, a transcriptionally silent region of the genome. And when we do that, so I'll try to put a droplet in this dense region of the genome. What you see is that these red droplets do not go inside that heterochromatic region. Instead, they decorate the outside of it like flower petals. And we think that that's a mechanical exclusion effect. We can actually simulate that together with our collaborators, Joel Berry and Miko Hataya. We can simulate that mechanical effect. We think it reflects this mechanical energy deformation contribution to the phase behavior. So I'm just about out of time here, so I just want to make a couple last points. One is that these droplets can still pull genomic elements together through coalescence. And we can see that here, and we think we're able to use that to actually measure some of this mechanical stiffness of the genome. What that means, though, is that the droplets, if they're attached to particular genes, they can pull them together through coalescence and actually activate genes that way. But non-specifically interacting parts of the genome are excluded through this exclusion effect that I showed. So we think this is a kind of way in which phase separation is rearranging the genome in a kind of smart way, filtering out the non-target regions of the genome and bringing together the target regions. So I'll try to tie this up here now. At the beginning of the talk, I told you that a key kind of poorly understood part or length scale of biological organization is this mesoscale level. We think that liquid-liquid phase separation is a key aspect of organization on that scale. We think many of these organelles, really dozens of different types of organelles in the cell, are assembling by liquid-liquid phase separation. There's a lot to figure out, and there's many ways in which we think there's going to be new physics at play that go far beyond the sort of equilibrium statistical mechanics pictures that we're using now, because that's kind of what we have. And I think that the multi-component non-equilibrium features, it's a whole playground for condensed matter physics, and I hope you'll so I think I mentioned key individuals as I went through the talk, so I won't list system again here, but I just want to thank our group. We have a really fantastic interactive group, and I'd like to thank people who funded us over the years, and thank you again for your attention.
Wonderful. We have some time for talks. Yes, please, over on the right.
Professor Brangwyn, thank you very much for certainly one of the most beautiful talks I've seen this week. Congratulations on some amazing discoveries. I had a couple of questions on some of the details of the phase separation. So you showed some pictures of spinodal and monodal decomposition, and then the more classic balancing the surface energy versus the bulk energy to drive the phase separation. And so in that movie that you had of the droplets that were trapped in the actin network, that essentially prevents the droplets from coalescing and growing that way. But you would also expect if this were an equilibrium process that you might see the analog of some Oswald ripening, where smaller droplets disappearing at the expense of the big ones, and the actin network would prevent the coalescence. But you should still imagine some distribution, maybe for smaller droplets disappearing. So is that a sensible way to look at it? And I didn't see, at least in the movies I saw, do you see small droplets disappearing while the larger ones grow in cases where coalescence is blocked?
Yeah, this is a good question. So Oswald ripening effects, we think are playing a role, and so we explored some of that with the nucleolus in the experimental system of the C. elegans embryo. In the frog oocyte system, you don't usually see shrinking of those droplets, the small ones at the expense of the large ones. I mean, the Oswald ripening effect, as you know, is ultimately mediated by surface tension, and these surface tensions, as for other macromolecular liquids, tend to be small. So you sort of order of magnitude say the surface tension would be kT over some molecular length scale squared, and these are macromolecules, so the surface tensions tend to be low. And so we think that Oswald ripening is less important here than maybe in some other systems.
You would expect proteins to diffuse through, these distances between droplets and course in that way.
Yeah, I guess what I'm saying is there are places where we think Oswald ripening is at play, but in that frog oocyte system, we don't usually see that. And I think most of the droplets themselves are already quite large, and the surface tensions are small, so we think it's less. That's why it's not visible there.
Yeah. Let me take a question from the left-hand side.
Hey, Cliff, it's Sarah.
Hey, Sarah.
I want to learn a little bit more about the nucleolus. Is it always the case that you have NPM1 and tubular phase separating within the nucleolus, or is that only under particular conditions?
Yeah, so that's generally that's what you find in the textbooks, and that's what we see in these systems. I mean, they are in separate compartments. I mean, there's some partition coefficient, right? So you can have some NPM1 within the MC, within the triple iron rich, and vice versa. And we actually are actively studying, the partitioning and sort of the physics of partitioning, if you like. But yeah, that's not induced. There is a way to induce a sort of a higher order demixing if you turn off RNA transcription, which I can tell you about offline, but that's the native state.
Okay, cool.
Yeah, good.
I think I'll request further questions, hopefully right after this. I'd like to thank the speaker and all the speakers.
Yeah, I'm also very honored to be chosen as a speaker for the Kepler Symposium. I want to really thank the Kepler Foundation and the committee who selected me for the speech. And I have to thank especially the chair for giving me this complex title. So the title was not my choice. So the title came from the chair. And first I thought, is it? I was telling, oh, okay. But anyway, I thought, no, it's a really fantastic title because it says more or less everything what I want to talk about. So I want to explain you maybe don't know Heusler compounds. I want to explain you. Then I want to explain you how I can use the periodic table as a Lego box to build maybe most of the states you are interested in. So I'm at the beginning of the symposium, so I'm talking about the unit cell. So I have an easy game because the unit cell is quite simple compared to the complexity of biological cell. But I think it's easy then also to go with the next talk because I use some of the features like topology to explain the properties of my material. So I'm talking about a family of compounds, Heusler compounds, which have a simple cubic unit cell. If you see there, all the three lattice constants are the same, and you have a few atoms there. It looks quite simple. The other thing which I want to say, 2019 is an important year because we have two celebrations, and one is the celebration of 150 years of the periodic table, and because Mendeleev wrote the periodic table down. You see here an example of the periodic table, but there are other possibilities, and as you see, also Lego, this is an official periodic table which I found in the internet, Lego periodic table. The second celebration we have in 2019 is 125 years of Heusler alloys. This compound were invented by Fritz Heusler, you see here in the photo, and he was an owner of Kappa-Mine, and the company which made alloys of copper and manganese to make chemicals. In his free time, he mixed some additional elements into the compound, and manganese, copper, and aluminium, we know, are non-magnetic, and he mixed the three elements together, and he was surprised because the result was a ferromagnet at room temperature. So this is a surprise by itself, and we have a few toys, only 3 toys here in the room if somebody wants to see. So you will see copper, manganese, and aluminium are non-magnetic in your plastic box, but the Heusler alloy is a ferromagnet at room temperature. So the compounds very often have nothing to do with the elements they made from. So then I come to the next part. So as you remember, now you understand what the Heusler compound is, a simple cubic compound. So we have the Lego box, and our elements of the periodic table, they have a certain color, and the color is related to the atoms. You see, we have here green, blue, and red balls for the Heusler compound, and all the elements which are available for the green position are here in green, all the elements for the red position in red and the blue. And now the mathematician in the room can calculate how many possibilities we have to make new compounds. So I can retire on Heusler compounds. Okay, and this is the way we do it. Here you see me and Fächer, my old assistant, trying to make new Heusler compounds. So we have our periodic table, and you see there are some elements around in the periodic table, similar like the toy box maybe you have here in the room now. And then we choose which element we combine and what we try new. So there are two different types of Heusler compounds. One are the so-called half Heusler compounds with the composition 1, 1, 1, X, Y, Z. So there are 3 interpenetrating FCC lattices, and then there are the Coulter compounds with the composition 2-1-1. They have 4 interpenetrating FCC lattices. So quite simple, but we can do a lot with this material. The way we do it in our group is, so somebody designs material on a computer. In our case, density functional theory works quite well. Then people grow single crystals, do thin film growth, and some other people do the investigation of the property. So what is still missing is we want to design the state. So I have chosen a Hamiltonian who looks quite complex to show you how I can design this material for a certain property. So here we have a Hamiltonian for magnetic system, which consists of Heisenberg exchange, Jagodzinski-Moriya, magnetic crystalline anisotropy, and dipole-dipole interaction. So I want to show you how we found our fermion system by using this Hamiltonian and the way we can tune Heusler compounds. So the fermion is a spin texture, so spins are important, therefore magnetic systems are important, and it's very complex, and the texts are even more complex than the very famous Bloch fermions, and it's a mixture from Bloch and Niels fermions. You can see it here on the screen. It looks quite complex. Okay, so first we have to understand maybe the 1-1-1 Heusler compounds because they're quite simple. So you see this is a third structure here on the screen. So they're more or less relatives of silicon. You know, you have silicon in the diamond structure, but the disadvantage is you have not so many possibilities, for example, to tune the band gap. Therefore, people already did binary semiconductors. This is the example of zinc blende here on the screen with 2 elements, 2 balls, green and red. And in case of the Heusler, we go simply to 3 elements. Okay, you have more trouble with this order, but you gain a lot because you can tune the band gap and many other properties even better. So the next periodic table I luckily found from the University of Wisconsin. They have a periodic table even to teach school students chemistry. So here you see the elements have even a second blue layer, and the blue layer tells you the elements from row 1 have 1 electron, therefore they have 1 blue dot. The electrons from row 2 have 2 dots, and so on. Okay, and but it shows also nicely why we, for example, have sodium chloride as a stable white band gap insulator, because sodium has 1 electron, chlorine has 7. There's 1 missing. You see this white dot in the lower corner of chlorine, and they together build sodium chloride, which has the same 8 valence electrons like argon. So this is how you know you build binary semiconductors. We have 3 5 semiconductors because we take gallium with 3 electrons and arsenic. The sum is 8, so we are happy. So we have a full shell of 6 of S, 2 S electrons and 6 P electrons. Okay, so but now you can imagine how we do this with 3 elements. There's no magic. Okay, we distribute 8 electrons over 3 elements like lithium, magnesium, arsenic, and you see how we do this with the Lego toy. We have simply the blue dot for lithium, red for magnesium, and 5 electrons again for arsenic. But life would be easy if we would not have the transition metals. Every physicist in condensed matter knows the interesting stuff is with the transition metal. They have d electrons, and this is the advantage of the Heusler compounds because we can even play with transition metals. So we can, for example, make a semiconductor like zirconium nickel tin. Surprise! You take 3 good metals, zirconium nickel tin, nickel. You would even think eventually magnetic. But in total, we have 4 electrons from zirconium, 10 from nickel, 4 from tin. So we have 18 valence electrons. So we have now the S, P, and the D electrons. So we stay semiconducting. So we even can grow the single crystals, as you see here, as nice, beautiful single crystals. And we can do band structure calculation. You see here there's a gap between the valence and the conduction band of 0.5 eV. Then you can do even Engel reverse photo emission, which is like we photograph the electronic structure, and we see it's a little bit larger, but this we expect from DFT. So with our zirconium nickel tin, we really have a nice semiconductor now with 18 valence electrons because the bonding states are SPD in this case, and it's separated by the gap from the antibonding states. So we can even make, and this is a nice result from Alex Summa, a 2 eV band gap from very strange elements like tantalum, iridium, germanium. So I was really surprised, and I nearly didn't believe it when I saw this result. Okay, so now to become tetragonal or hexagonal. So I can strain it along the 100 direction, then it becomes tetragonal. If I strain it along the 111 direction, it becomes hexagonal. So it becomes crystalline anisotropy. And this is a precondition if I want to have a magnetocrystalline anisotropy, because then my spin of my atoms, my magnetic atoms, will have a certain direction. As you see already here in my drawing, they are nicely out of plane magnetized. So why is this interesting? This is maybe interesting even for the chair, because he likes to find hard magnets. And if in the moment, if I have, for example, a tetragonal structure which has a crystalline anisotropy, I also have maybe the spins out of plane magnetized, and this leads to a hysteresis. So if I draw a hysteresis in the magnetic field of my material to a hard magnetic behavior. So here's an example with thin film on the, I always have to take your perspective on the right side of my slide. So you see so I go with the doping of my compound from manganese 3 gallium to manganese 2 cobalt gallium from the upper part in the first panel to the lower part in the second panel. And you see in the first slide nicely how you have an anisotropic magnetic structure. You have hard. If you measure out of perpendicular, you see a hysteresis. If you see this in-plane and out-of-plane magnetization, you see no hysteresis. And you can even dope it to very large hysteresis, which is a very large coercitive field, but a small moment here on the lower part, and then it becomes soft magnetic in cubic again. Oh, sorry. I can even predict this by theory. So if I, for example, look how the magnetocrystalline anisotropy is for different materials of the composition manganese 2xy, so I can distinguish between in-plane and out-of-plane by doing DFT calculation. Here you see the energy, the magnetocrystalline energy above above 0 is in plane, below 0 is out of plane, and again it's a number of valence electrons, and you see it works again quite easy. I can forget about doing the calculation because it goes more or less with the valence electron. But what you see here also, if I have heavy elements, like you see the red lines are 3D elements, the green lines are 4D elements, and the blue ones are 5D elements. So if I become more heavy, relativistic effects play more a role. So I think also the magnetocrystalline anisotropy, the out of plane magnetization has a higher tendency. But I can also design now, and this is what is interesting for me, if I want to have fermions, I want to have quite a complex spin structure, and then I want to have not simply in or out of plane, I want to have compounds which are at the borderline, which are then showing a non-collinear spin structure, because this is what we have to look at. So by increasing the spin-orbit coupling and going from 3D to 4D to 5D, I change the Dzerjinski-Moriya interaction at the same time, and magnetocrystalline anisotropy. So now I more or less have without the dipole-dipole interaction already worked on 3 parts of my Hamiltonian, and I have the material. So the material is manganese 2 or 1.4. This is a little bit more complex because of the phase diagram, platinum tin. So this compound shows the nice non-collinear spin structure and shows the complex magnetic phase diagram which I need if I look for skyrmions. And it has even the right symmetry, D to D, which I need for antiskyrmions. So now I have my prediction, the antiskyrmions, my compound, and then Stuart Parking, he looked in in Lorentz transition electron microscopy, and there you can see the complex spin structure. And if you see my antiskyrmion looks a little bit like a d orbital, and in reality it looks also very nice, like a d orbital. So this is, I hope, I convinced you how to design the state you're interested in. So I have quite a good phase diagram to look like the states are stable, or high beta stable, even at the 0 field and at high temperature, since Stuart is always interested in spintronics, he wants to have root temperature application. So now the next step is, what is the meaning of the dipole-dipole interaction? So for this, this group of Stuart has made a wedge out of our single crystal, and with this wedge, because it seems to be that the mesoscopic structure plays a role in this compound, the shape anisotropy in this compound, he could even tune the size of the skyrmions. So here you see the skyrmions on the wedge, and you see if the wedge becomes thinner, the skyrmions become larger, and also the domain structure becomes larger. This is the role of the dipole-dipole interaction. So I'm at the end. So I cannot now summarize extensively the unique parameters of the Holzer compound, but you can read it in the Nature Review Materials article. But I hope I have convinced you that you can do quite a lot, playing with topology, getting insulated, topological insulated, light semi-metal, direct semi-metal spin, ferro, antiferromagnetic, compensated, non-collinear, and so on. Holzer compound. Okay, so now you know you can do quite a lot with Holzer compound. Okay, and with this, I thank you for the attention, and I think this is a little bit to give you the idea what you could do in application with the Holzer compounds, like thermoelectric. They're quite advanced in thermoelectric, magnetocaloric, magnetic cooling, but you can also have interesting properties in spintronics, etc., and hopefully soon also in quantum properties. If we could make quantum anomalous Hall effect out of Holzer compounds, since the TC is quite high, this would be really cool. Okay, with this, I thank you again for your attention, and I thank my co-workers and my group for helping me to get all this nice results. Thank you very much.
Thank you, Claudia, for a informative, entertaining, and nutritious talk.
That's trivial donut and the topological here, so I forgot to distribute it.
All right. We have time for a question or two if someone would have a burning question. There are mics, I think, in the aisles. Or as Claudia predicted, this is often not the venue for questions, but I do encourage you. Nope. I see. Yeah, come on, Greg, there are 2 here. Greg, come up and get one. All right.
So you have to ask a question. So what is your question?
Claudia is keeping the Ich bin ein Berliner
There's more donuts. Okay. If you give me a question, you get a donut. So what's it? Okay.
Okay. And the question is?
So I think the magnetocaloric effect, and this is your donut. It's trivial. Topological trivial. Anyway, so you have a transition from the cubic structure into the tetragonal structure, but you have to make sure that the structure matches. So one critical issue is that the hysteresis of the structure phase transition is small. And I think this is one of the challenges in Heusler, but thanks to some theoretical prediction even from shape memory alloys, I think we are now knowing how to optimize the lambda, another value, for optimizing the magnetocaloric properties. Maybe it works. Thank you. Okay.
Well, let's thank Claudia again. Oh, I'm sorry. Oh, Greg.
So the inclusion of transition metals at least helps move you towards higher energy scales at different temperatures. Is there sort of a strategy beyond that gets you closer to a temperature?
So since TC is already at 1000 Kelvin, some people now even using 4 transition metals for making Heusler. But then the bonding gets lost a little bit. So I like to have the non-magnetic glue. But there are also ferromagnetic Heusler compounds, but then the TC again because of the localization of the alpha electrons drop. So I think we are quite in a good. But I think the localization maybe helps us to make quantum anomalous Hall effect, So because we have to be closer to the semiconductor. But I'm quite optimistic. Okay.
Good. Thank you so much, Claudia. Well,
you very much, Roger. Thank you also, Donna, for this very nice introduction. You know, I have only talked about applications. About the field, you know, the people at the Stockholm said that they were judging only science. Okay, they were not in the Oscar business. Okay. So anyway, I think Donna, it's always a difficult time to follow Donna, you know, because she's so good at presenting things, and so I'm going to use that too. So anyway, the title of my presentation is really a passion for extreme light, and this is very easy to understand. You know, when we did CPA, we started with the CPA, and you know, it was a wonderful concept. We could really amplify. The first demonstration was at the mini-joule level, and then you know, we could really push it to the joule and have a joules, and every time the concept seemed to work. You know. Very intriguing to see how far we could go, and that goes back to one of the questions that Donna got. So anyway, what is very exciting, of course, are the applications. Okay, it's one thing to produce very high densities, but the application which follows are really mind-boggling. So I'm going to start. Does it work? Oh, okay. Wow, not too fast. Too fast. Yeah. So, like Donna said, you know, everything started, you know, with this man, Ted Neyman, okay? May 16, 1960, for the shop, laser shop. Anyway, and, you know, there's one thing which is really mind-boggling about lasers, is the fact that, you know, you can use light, you know, to slow down atoms, and you can slow down atoms to very, very, you know, small kinetic energy, microelectron volt, nanoelectron volt, these kind of things. And that, of course, led to the development of this beautiful field of quantum optics and cold atoms and so on. But also, what you can do, and this is really, you can do just the opposite. Instead of slowing down atoms, you can accelerate, you know, particles, and you can accelerate particles to very, very close to C with very, very large Lorentz factors. And that is really remarkable. And now we can really accelerate particles to the GeV, with no doubt that one day we are going to go to the TeV. So you can see that with one EV atoms, photons, I'm sorry, from the lasers, you can really go through about 20 orders of magnitude from the nano EV to the TeV. Okay, this is remarkable, and that, of course, you know, always fascinated me. And you know, there is a lot, as you will see, there's a lot of work, you know, about. So this is, of course, Chern-France amplification. I'm not going to describe it.